Okay. So, what I want to talk about today is about some asynchronous algorithms for matrix factorization that we have been developing. This talk is a little bit more technical and a little bit more raw than the other talks that you have seen so far. It focuses on a specific problem. And then towards the end of the talk, I also want to show you roughly how this scheme that we have can actually be extended to a bunch of other things, including some very general machine learning problems. Okay? So of course, you've been hearing a lot of talks about machine learning, and what we really want to do here is to build a model which can predict well on data. Of course, the challenge here, you want to say, okay, how well is this model doing? And one way to evaluate it is to use a loss function, right? So if it's basically some sort of a discrepancy score. And the biggest challenge that machine learning experts face is that this model has to generalize to unseen data, right? And so one way to avoid overfitting in this kind of data is to use a regularizer, okay? So this is sort of standard. And one potential framework in which you can do all of this and build a variety of different models is regularized risk minimization. So the idea here is that you have a loss function which says how well your model is performing, and then you average your loss function over your data, and then you add some kind of a penalty function, and lambda is this parameter which trades off between the two. Okay? And then there's a bunch of things that you can express in this framework. And what I want to do is start from here and then go towards something very specific, which is basically talk about collaborative filtering or matrix factorization. Okay? Now, of course, the holy grail in machine learning is how do you solve this regularized risk minimization problem at scale? Okay? And then there's this whole, you heard a bunch of talks about how MapReduce was something that was useful for a while, but now everybody doesn't want to do MapReduce because we all know where the issues are. So let's try and see how we can avoid some of these issues. Basically, the key idea here is how can you avoid bulk synchronization at every stage when you're learning a model from these kinds of regularized risk minimization type tasks. Okay. So let me start with something very simple, which is collaborative filtering. Okay, so of course at Amazon we are also interested in a bunch of users, say maybe a bunch of movies in Amazon Instant Video. Some people like those movies, watch them to the end, others don't like them, and so on and so forth. So we have lots of feedback about what users like and what movies they like. And of course the question is that what movie should I suggest to you? Okay, and Carlos already alluded to this problem in the morning. And one potential way that you could think about solving this problem is by using what is known as matrix completion. So basically you assume that this matrix A, which is the matrix of the ratings, is sampled from some unknown distribution, and basically you're trying to complete the other entries which you haven't seen. Okay, and one way to do this is to take all your users and embed them into some low-dimensional space, take all your movies, embed them into the same low-dimensional space, and then try to and take a dot product in this low-dimensional space and say the dot product predicts for you what the rating for the unseen movies is. Okay? So if you want to set this problem up, here is how you could do it. Okay? So you could say, okay, here is an optimization problem, here is an regularized risk minimization problem again. Here is your regularizer, which says that in the embedded space, I want the lengths of my embeddings to be small. Okay? And here is the loss, which simply says that on all the observations that I've seen, on all the ratings that I've already seen, the dot products must be close enough. Okay? And then this is a loss plus a regularizer. Now, if you look at this, this big objective function, one way to solve this, and this is by no means the only way, is to use stochastic gradient descent. Okay, so what you do in stochastic gradient descent is you take this big, large optimization problem, you say that I'm going to approximate this objective function at every iteration. So instead of computing this summation over all the observed entries that I've seen so far, I'm just going to approximate it by taking just one entry and then applying some sort of a gradient step on it. Okay, so if you compute the gradient of this one entry approximation, you get a gradient which looks like this. Okay, and the stochastic gradient descent updates therefore look like can be written in this form. Well, what I want you to think about is don't worry so much about the math, but sort of pay attention to the structure of these equations. Okay, so what does this tell you? that in order to update the W, the factor for one user, the ith user, I need to know the factor for the ith user, and I need to know the rating, the jth rating that he gave, okay, which is Aij, and I need to know the factor for the jth movie. Okay, so this is the only two pieces of information that I need: the factor for the user, the factor for the corresponding movie, and the rating. If I have these three pieces of information, I can do this update. Okay, so that's the observation here, and the same, the identically similar things for the for the movie vectors as well. So this inspires the following simple idea. This was presented in KDD 2011, which is, why don't we take this big matrix that we have of the ratings and distribute it across multiple machines, okay? And then what you can do is that, so let's say these are all your users and these are all your movies. So you can have each machine work on a subset of the users and a subset of the movies. So here, for instance, the first machine works on all the red subset of the users and the red subset of the movies, okay? And therefore, you can choose any entry, any rating in this part of the matrix, and you have the user matrix, you have the rating, you have the user embedding, and you have the item embedding, right? So the three pieces of information that you need in order to make an update with respect to that entry of the matrix. So this machine can happily continue working on this portion of the matrix. The second machine can continue working on this portion of the matrix, and so on and so forth. And after a while, you stop, you synchronize. Okay, what do you mean by synchronization? Everybody communicates to each other and communicates the movie parameters across all different machines. Okay, so now after communicating, now all the movie parameters have moved to different machines, and now this machine can continue working on this part of the data, the other machine can continue working on the other part of the data, and so on and so forth. And again, you can synchronize, communicate, and so on and so forth. So the good thing about this scheme is that, of course, it's very easy to do in MapReduce, and you can nicely parallelize it. But again, the problem is this bulk synchronization, right? You have to synchronize after every step. So what happens is that if you look at the way you're using your resources when you do this kind of an update, is that, of course, your communication and computation are interleaved. So when you're communicating over the network, which is when you're transmitting all these parameters to other machines, you're not computing, right? And when you're actually computing, your network is idle. So basically, you're hammering your network, then you're hammering your CPU, then you're hammering your network, you're hammering your CPU. Okay? So the question then becomes, is there a way that we can use in order to keep both CPU and network simultaneously busy in this kind of a problem? Okay? And here is a simple solution which we call NOMAD. The name for this algorithm becomes clear in a couple of minutes. So here what happens is we start in the same way. You distribute your parameters. So here are all your user parameters. Here are all your item parameters. Okay, and you start in the same way as before. So this machine is continuing to update using data from this part of your ratings matrix. The other, each of these machines is working on their own part of the data. But now the twist is that at some point of time, while this computations are happening, say the first machine may decide that it is going to take out one of its columns, which is one of the item features, and gossip that parameter to some other machine. So in this case, the first machine decides that it wants to take this column, which is the item features corresponding to, say, the second item, and pass it to the fourth machine. Okay, so you just choose a random machine, you communicate this column to it. Okay, while this communication is happening, you do not need to stop your computation, right? So the first machine is still computing, but just this one column is taken and passed over to the other machine. Once the other machine receives this, now it has data, so it has all these user parameters, and it has the corresponding item parameters, so it can start sampling using these entries of the matrix as well. Okay, and then the same scheme continues on and on. So basically the idea is that at any point of time, you have these machines which are doing their updates on the portion of the data that they have and on the items features that they have. At some point of time, asynchronously, without waiting for any sort of synchronization, they pick one of the item features and they transmit it to another machine. Okay, and this happens completely asynchronously. There is no synchronization at any point of time. Okay, so, and because of this, your CPU and your communication are not interleaved anymore. They're happening simultaneously. So you're hammering your network and you're hammering your CPU both simultaneously at the same time. Okay? And this just keeps going. Okay? And eventually you will have that. All the columns would have visited all the machines, and therefore you would have updated on all entries of the matrix, and therefore you would eventually converge. So how well does this work? Actually, it works amazingly well, much better than we thought it would. In fact, if you look at something like the Netflix problem, you get super linear speedup. So we were actually wondering about how is this that you get super linear speedup when you actually throw more machines at the problem. How is it that things are actually getting better? One of the possible explanations for this is because there is so much, when we are doing the updates, we are hitting the memory throughput of a single machine, but when you actually distribute the updates across multiple machines, the memory throughput is much higher, and therefore you get better performance. And the same thing happens, so now I just want to show you basically as sort of the bang for the buck figure, which simply says that if suppose I took the elapsed seconds into the number of processors, so how much time, how does the test RMSE vary as I take the number of processors multiplied by the elapsed time, which is basically the true CPU time that I spent. In terms of that, how does my RMSE vary? So if I go to 2 processors, 4 processors, and so as you can see, as I get to more and more processors, actually I get better and better bang for the buck. Okay? So this is on the Netflix data set. Here, this is another data set, which is Yahoo Music. Here you don't quite see, there is some sort of a plateauing happening, and this is something that we are still investigating. There's some unholy interactions between Intel TBB and the memory bus and MPI, which is causing this problem. So we are still sort of investigating this. But again, I want to show you the same kind of thing. Again, this is a third data set that we tried, which is about 5 million users, 200,000 movies, and we have about 270 million non-zero. This is a synthetic data set, and again you see this kind of super linear speedup. Okay, so the basic idea here is that if you can keep your CPU and your network busy simultaneously, then you can potentially reap benefits, big benefits out of this. Okay? Now, what I want to show you next is something that is very, very new. I mean, this is something that where, literally I was running experiments in the morning, and some graphs that you see are as fresh as that. But I'm very excited by this. Okay? So the question is that the particular structure of the matrix completion problem, where there were users and items and they were interacting in some bilinear fashion, was very important in order to do this kind of an asynchronous communication that we saw previously, right, in NOMAD. Now the question is that, can you do the same kind of thing? Can you employ the same trick to solve a larger class of regularized risk minimization problems? Okay, and it turns out that this is actually something that we are very excited about. And it turns out that if you take the regularized risk minimization problem and sort of massage it in the right way, then it turns out that you can make this work in a way that you can employ the same kind of structure. Okay, so let me show you how the massaging works. So you start with the basic problem formulation that we had, which is the regular. So again, note that here I am actually deliberately not specifying the loss function. Right? The reason for this is because by plugging in different loss functions, you can get different sorts of algorithms. Right? So if you plug in the hinge loss, you get SVMs. If you plug in the logistic loss, you get logistic regression. If you plug in more structured losses, then you get structured SVM and so on and so forth. So there's a variety of different algorithms that you can build by just using this framework. Okay? So you start with this, and you rewrite this in the following way. Okay, so you simply say, okay, I'm going to introduce this one new variable, UI, and I want to keep UI to be equal to w.x. Now I'm going to take this UI into the objective function by using a standard trick, which is using a Lagrange multiplier. So now I actually have 3 different sets of variables. So I have the w's, I have the u's, and the alphas. So it seems like I'm making my life unnecessarily complicated, but you'll see in a minute why this is useful. So now the next thing I can do is that I can switch the max and the min as long as the problem is convex. Okay, so if the problem is convex, this is a standard trick, and I can switch the max and the min. And if I switch the max and the min and I eliminate u from this equation, okay, then I get a form which looks like this. Okay, and if I use standard Fenchel duality, then I can replace this part, which is the max of L ui plus alpha ui, with the Fenchel conjugate. Okay, and now I get a form which is actually which actually looks a little bit more beastly, but and has 2 sets of variables: the primal variables w and the dual variables alpha. But it turns out that I can write this problem in a really nice way, which is as a summation problem. And the stochastic gradients for this problem also have the same decomposing property that I talked about before, which is to update one coordinate of w and one coordinate of alpha, you only need to know the non-zero entry corresponding to that particular coordinate. Okay, so the problem decouples nicely, just like before. And you can pretty much apply the same trick that we had, and now there is a variety of different problems, a variety of much larger class of problems which you can solve in exactly the same way without synchronization across machines. So I don't have, as I said, this was something that I was working on. I just have one plot to show you that it actually converges. So if this is just a very, very preliminary result, so take it with a grain of salt. But I'm very excited by the possibilities that this opens up. With that, I just want to thank my collaborators, Inderjit Dillon, Shin Matsushima, Cho, and Xiangfu, and Hoikun Yun. Thank you very much.